This week, we're going to talk about energy getting into the earth. Up until now, we've just looked at observing the weather, talked a little bit about what the weather is, the atmosphere is. Well, starting this week, we're going to start bringing energy into the atmosphere, and then we're going to try to figure out what happens with that energy, because that is the main control of what the weather is going to do. So, how does energy flow in and out of this orbit? And how does it keep it stable and habitable for us so we can live here? Well, let's look at little things here. Electromagnetic radiation. You all have listened to the radio, hear satellite radio broadcast, done microwave cooking. All of that is electromagnetic radiation. So electromagnetic radiation comes in a lot of different forms. And one of those forms it comes in is sunlight. It comes from the sun. So let's learn a little bit about electromagnetic radiation. It's a wave, it has a wavelength. If you're in the ocean, you ever feel ocean waves hit you, then the water kind of goes down and then it hits you again with a bigger wave the next time, maybe. The wavelength would be the timing or the distance between those two wave tops. The same thing holds for the electromagnetic waves. They are waves of energy moving through the atmosphere, and they have a top, a bottom, where they go down lower and they come back up again. How frequency of a wave is if you're at one point, how many waves pass you in a second? The more that pass you, the greater the frequency. And interestingly, all electromagnetic radiation moves at the speed of light. So they're moving at 186,000 miles per second. So we have things like radio waves that we're all used to, microwaves we just talked about, or another one, ultraviolet radiation or visible radiation from the sun. And there's infrared radiation that humans, the earth, anything that has any kind of heat puts out. So in order to simplify what we're going to talk about here, we're going to make an approximation. We're going to make the approximation that overall, the earth is a black body, and most things on the earth are black bodies. What does that mean? Well, if you have an object that is at one temperature, all the radiation that comes into it from the sun, wherever, that hits it, it receives it, and then re-emits all that energy back out so that it never changes its temperature. That's a black body. Makes laws a lot easier to use in the radiation spectrum. And we're going to talk about some of them here. We approximate that the sun and the earth are both black bodies. So one of those things that we get from that is Wind's displacement law. So it says the wavelength of the most intense radiation, we talked about wavelength being the top to the top of waves in the atmosphere or anywhere, is proportional to the temperature. So if that's the case, then the hotter the temperature, the more frequent the wavelength. So that you would have temperatures like you and I at 75 degrees would have one wavelength, and you would have temperatures that coming out of the sun, that's at 1,000,000 degrees or so, would have a completely different wavelength. So that's why we have the ultraviolet wavelengths and the visible spectrum that come from the sun, infrared spectrum that we can't see, but that comes from people and plants. The next law is Stefan Boltzmann. What he determined was that the energy from an object, a black body, is proportional to its fourth power of its temperature. So, if you're on Earth, average of the whole Earth's temperature is probably about 28 degrees, about 21 to 20 degrees Celsius, we'll say. Now, if you were on the sun's surface, you're way higher than that, many times higher. So if you did it to the fourth power, you can see a tremendous amount more energy is going to come out of the sun than comes from the earth. Finally, the distance from the sun. If we consider the earth at 1 unit, so that E of energy coming is going to double with the distance from the sun. So Earth is one distance, Venus is closer, so it isn't even a 1, it would be like a 0.6 or 0.7, but Mars is almost twice as far, so if you have it twice as far, it only receives a fourth of the power from the sun. So the further out you get from the sun, very quickly the amount of energy is being lost. All right, the sun is basically a big nuclear reactor. Uh, it's a fusion reactor, which is very different than atomic bombs that we've used with fission. And all power plants right now on Earth are fission power plants. So again, we're splitting atoms there. Here, you're actually combining atoms. And the sun is very good at it. And because of that, when it combines, there's a little tiny bit of mass that's left over. And according to Mr. Einstein, E will equal mc squared, where mass is times the square of the speed of light. So think about that. You have a very tiny mass. The speed of light squared is a huge number. So it doesn't take much to get tremendous amounts of energy. On the sun, you have the photosphere, which is the surface of the sun. It's cooler than the interior. And we have sunspots that rotate around that surface. They're cooler spots. And then we have the chromosphere, which is an area of the sun which is very superheated gases. These are the different spots on the sun. Interestingly, now that we've got all this energy coming from the sun, the Earth doesn't make anything easy when it comes to solar radiation. If you were to walk outside on July the 1st, or let's say June 21st, when the sun is the furthest north it's going to get, and looked up, the sun would be almost overhead directly. It's still not quite. And you can see here in this slide that we have A, where the sun is directly overhead, and B, where it's coming in and out at an angle. Notice the sun, we'll say, is the light area, the radiation it's sending your way, the energy. The smaller the circle, the more intense the energy. The bigger the circle, same amount of energy, it's just got to cover a larger area. So that means that where you're not getting the sun directly overhead, you're never getting as much energy as that area. So in our case, in the wintertime, the sun is all the way down 21 degrees south of the equator. Angle is much greater, so we're receiving a whole lot less energy. Keep going north up into Canada, or even all the way to the North Pole. North Pole doesn't even receive any energy in the winter times. So you can see all of a sudden all this sun's energy, instead of getting distributed nice and evenly over the earth, is not. There's more of it coming down near the equator than there is further north or south away from that. And here you can see how it changes with time. And interestingly, that change doesn't happen because, oh, the earth is tilting back and forth. No, the earth stays the same tilt here or here, but one way the sun is directly in the southern hemisphere, and on the other side of its orbit around the sun, the earth is tilting towards the sun on the northern hemisphere. So that is why during the course of a year, parts of the earth get significantly different amounts of radiation. And yes, the sun is closer to us in the wintertime, but it really has no impact whatsoever. It's a very tiny amount of difference. Now, we go to the atmosphere. It's not exactly transparent solar radiation. What does that mean? Well, as the solar angle gets low angles of incidence, has more and more atmosphere it has to pass through. So when the sun is directly overhead at noon or close to overhead at noon, it's passing through less and less atmosphere. When it's setting, it's passing through more atmosphere. Oh, yeah. If I'm over the equator, it's passing through less atmosphere. If I'm at the North Pole and say the sun is just starting to rise there, it's passing through a lot of atmosphere. That makes a huge difference on the amount of energy getting there as well, as we got to deal with things like scattering, reflection, absorption. So you can see here, this is just an indication of how much solar energy is arriving. Notice at the equator, not a lot of change throughout the year. Antarctica goes down to zero in our summertime and comes back up as we're getting into the fall. And then we have mid-latitudes, like in this case, Rockport, New York. You can see how it changes and goes down lower in the winter and higher in the summer. But significant change in the amount of energy you're receiving. And these are just pictures of where the sun is brightest. You can actually see the sun picture from space where it's making the most reflection. And because of that, it's actually changing the amount of time that the sun is up. So if you're living near the equator, we're having almost always a 12-hour day, just a little bit of change. The further north or south you go away from that, summertime is going to be much longer, hours up, the sun's going to be up longer. Wintertime, the hours are going to be less, the sun's going to be up less, until eventually you get to near the North Pole, the Arctic Circle, and you're going to get, wow, the sun stays up all day during the daytime during the summer and is not up at all during the day in the wintertime. So what happens? We talked about that moving through the atmosphere. So part of that solar radiation that's coming in is absorbed by the atmosphere. Another part, and also absorbed by the earth. Another part is scattered or reflected. You ever see the beautiful blue sky we have here some days? That blue sky is scattering of that radiation. And another part is handled by the earth itself. So scattering can be in that form of what you see in the blue sky, but also can be from clouds or dust particles in the atmosphere. It's a very dusty day. You see all that haze? A lot of the atmosphere's radiation is getting scattered back into space or back towards Earth. It goes in all directions equally. Reflection. Look at a cloud from on top of it, or look at snow. Snow is the best example. You've got to wear sunglasses when bright sunshine comes out after a fresh fall of snow, or you're going to go blind from the brightness. Well, that is all albedo, the sun's radiation getting reflected back away from Earth. Absorption. Now we're bringing the sun's rays into our atmosphere and doing something with them. In the stratosphere, there's a major chemical reaction that takes place with ozone that protects us from the ultraviolet radiation reaching Earth's surface. And that protection actually keeps us from getting skin cancers more and having real trouble living on Earth with all that ultraviolet radiation is not good for people. So when we started losing that protection back in the early 60s, we started discovering it in the late 1970s. We really began to understand what was happening so that we understand now that there are chemicals that we were releasing basically from CFCs or halons, which were part of all the air conditioning systems we had and heats, sometimes part of HVAC systems. They're all gone. Most of them all over the whole world have been stopped using. But it takes a long time for that stuff to get out of the atmosphere. But they entered it. And what they did was they reacted with the ozone. So what happens in the wintertime, and it can happen in the Antarctic and it happens in the North Pole. More of an extent in the Antarctic is a polar vortex that forms. It cuts off basically the Arctic atmosphere from the rest of the globe. The same thing happens in the northern hemisphere. Unfortunately, ours broke down this few weeks, and that's why we're getting such extreme cold. But that area gets extremely cold, that polar vortex. When it gets so cold, things begin to happen with CFCs, they discovered. What happens is they break down and they begin to combine with the ozone. When they do that, all of a sudden, we lose a lot of ozone. So that's why we had to stop using them. Here's just an example of the albedos around the world. You'll notice the albedos of the ocean are much less. They absorb a lot of the sunlight compared to the albedos of snow or even sand. Here is actually what happens you bring a beam of light into the earth from the sun, 30% of it is reflected. 23% is absorbed by the atmosphere, and another 47% is absorbed by the Earth's surface. Those last two parts are what's going to heat the atmosphere, give her higher temperatures or lower temperatures, heats the Earth's surface. And here you can see how that works as it's coming through the atmosphere. The ozone layer and other layers in the atmosphere are areas like the stratosphere we talked about it warming. Well, what's happening is that ozone, those chemical reactions are heating the atmosphere. They're absorbing ultraviolet radiation. And instead of cooling, like you would expect the atmosphere to do, it's warming. There's another part to the Earth. If you did not have greenhouse gases, we couldn't live here. Greenhouse gases cause the Earth to stay warmer than it should. What is a greenhouse gas and why does it do that? All right, we hear tremendous amount of discussion about climate change and the impact of greenhouse gases. Well, let's learn a little bit about what that means, what you're talking about, instead of just hearing it. What you're talking about here is there are gases in the atmosphere that absorb infrared radiation but do not absorb ultraviolet or sun radiation or visible light. So what happens is all the sunlight comes in, the Earth heats up and transmits out infrared radiation, different wavelengths. These gases will take that wavelength, absorb it, heat up that gas, change its composition, maybe a little bit even sometimes, and then transmit that both up and down, that infrared radiation. So some of it comes back to the Earth and some of it goes out into space. By having some of it come back to the Earth, we're heating the Earth more. That's all that's happening. So the net effect of that is we wind up warmer than we would normally be. So here are the main greenhouse gases. Water vapor is actually number one. We're going to talk about something that water vapor happens in the atmosphere, and that is that the hotter the air is, the more water vapor it can hold. So you're actually going to increase a greenhouse gas the hotter it gets. The next most important one is carbon dioxide. Then ozone and methane. They're both lower on the end. Methane is extremely efficient at grabbing infrared radiation and sending it back. It's probably the most efficient, but there's not that much of it. So the radiation comes in, passes through with little effect, gets to the Earth, heats it up, Earth warms, sends back radiation. But now carbon dioxide, water vapor, all grab that and retransmit it back to the Earth and let some go out into space as well. Where you can really see this, if you ever go to the desert at night, there's almost no moisture in the desert. All that sun's radiation that's come in during the day heats up the air very hot. Now at night, there's no moisture. Infrared radiation is just going back out into space, and the temperature is really cooling. You can get extreme temperature changes between night and day in the desert. Now, go down to the Gulf Coast or go into a rainforest what happens is you got lots and lots of moisture. So you wind up with, during the daytime, it gets warm, humid. At night, the temperature doesn't drop as much. Why is that? Because of all that water vapor absorbing the radiation, keeping it warm. The calendar effect, it's just where a long time ago, back in the 1950s, they started measuring carbon dioxide. And you can see how it keeps going up statistically with time. And you'll notice on the bottom graph the seasons. Seasons impact this. If you think about it, in the northern hemisphere, there are more plant life than there is in the southern hemisphere. So in the summertime, we're going to actually absorb more of the carbon dioxide through photosynthesis, decrease it, then in the wintertime it builds back up again. Here's just some facts that have been studied, hypothesized, and then studied. These have been written up in papers that have been peer-reviewed and looked at by a number of different scientists to see if they're correct or not. So there's negative impacts to climate change. Agriculture. If climate change comes through as predicted, what it's predicting is one of the biggest things would be extremes. In other words, extreme amount of moisture coming in and the extreme amount of no moisture coming in, or extreme heat or extreme cold. The whole idea is there would be more extremes. So if that's the case, food, agriculture, human health, mean sea level rise, it's already happening. Ocean acidification and deoxidation, there'll be some longer growing seasons where ice is not a problem, will be greater. Decrease heating. So there are good and bad benefits to this. But sometimes too much of a good thing isn't always a good thing. And here you can see the changes that have been going on since the 1880s. Temperatures have been steadily rising, averaging about 0.12 degrees Fahrenheit. Not a big deal per decade. Now they're averaging 0.28. So you start extrapolating that. If it keeps getting faster, we begin to have a problem at some point. There are different ways of measuring radiation. Pyranometer is one. There are others we use. Satellites, infrared radiometers are used all the time in satellite. We talk about infrared satellites. So that is it on all this wonderful stuff coming in. One of the greatest ways to look at radiation coming to the Earth and out from the Earth is through our satellite system. I've given you a link to that, and I hope you'll use it. If you have any questions about all this, let me know.